Okay, epithelial transport of sodium. How do I get that sodium from that bag of Cheetos into my bloodstream? So what I'm going to do is use the cheapest, fastest rule and talk about each place you need to transport it. All right, so first place I'm going to need to transport it is right here. Across the apical or apical surface. So logically, it's going to be pretty high in the lumen right after I ate it. And anybody want to tell me why I can pretty much depend on sodium being low in the intracellular fluid of these intestinal epithelial cells? Because I work really hard on keeping it low, okay? So it wants to go high to low, but again, let's talk about cheapest, fastest way. Can sodium be diffused straight across the cell membrane? Nope, it can't. Again, the reason is that it is charged and polar. The cell membrane is lipid, it's lipophobic. So I can get it in, but what's the next cheapest way I could get it in? What is this protein right here? This is a leak channel or sodium channel, okay? That sodium channel, you can move it through a sodium channel, and that would be diffusion, right? So this is a channel, and the transport mechanism is diffusion, okay? So it's going to diffuse through a protein channel on the apical surface to get into the cell, but we haven't gotten it into the bloodstream yet. So now what do? Now what we need to do is we need to, the second step is we're going to move it across the basal or basolateral surface down here. How do I get it out down here? Okay, will it diffuse out? If not, why not? So what do we know about sodium's concentration? It's going to be, again, low in the intracellular fluid, but what should it generally be out here? It should be relatively high, right? Not because I just ate it like it was here, right? But because I'm constantly working, right? Because the lumen actually is an extracellular fluid. Okay, so it's going to be relatively high out here. And so now I need to get sodium to go from low to high. And if you want something to go from low to high, it's definitely not going to diffuse. So I'm going to have to actually send it through a carrier plus ATP, which is a pump. Okay, so I'm going to pump sodium out this direction. Okay. And this is a carrier plus ATP, which is a pump. It's actually the sodium-potassium pump, so it's using potassium at the same time. We just don't really care about potassium right now. And then once it gets into the extracellular fluid, again, this capillary is relatively porous, so it will just move straight in. That's just simple diffusion. Don't have to worry about it there. Now, what about potassium? Don't have to worry about potassium too much either, because potassium is going to be pumped in and leak out and pumped in and leak out just like it always does. Okay, so that is epithelial transport of sodium. Okay, now let's look at epithelial transport of glucose, for instance. So how do you get glucose into your bloodstream? It would also work for amino acids. So we're going to do kind of the same thing. This one really requires you to think about concentration gradients and transport and all of that stuff. And this is not memorization. It is something that I want you to understand. So epithelial transport of, let's say, glucose, because that's what this picture is. So what is the cheapest way I can absorb glucose? Let's say you just ate a delicious salted caramel chocolate chip cookie. How do you get the glucose into your bloodstream as cheap as you possibly can? So let's talk about that. So, all right, so I want to get glucose into my bloodstream because glucose is basically money. So I could, by the way, glucose might already be high in here, okay, because I've already got some in there, but I still want it in there, even if it's against the concentration gradient. So how can I get glucose to absorb? I want to absorb all the glucose I can because it's like the super valuable nutrient molecule, even if it's already high inside the cell. So the way that I will do that is via secondary active transport, so I don't have to pay for every glucose. And so what I'm going to do is I'm going to move it in with sodium, right? It's going to move in at the same time as sodium. What kind of protein is this? Is this a channel? Is it a carrier? Is it a pump? It is a carrier. And although it doesn't show it very well in this picture, it has a binding site for sodium and a binding site for glucose. And when they are both bound, it will move them both in, okay? So this first step is facilitated diffusion with a hitchhiker. So sodium is moving in. This time it's not going to move through a channel because I couldn't bring a friend through a channel. It's going to move through a carrier protein that has a binding site for sodium and a binding site for glucose. And the motivating factor for moving through this is sodium's concentration or electrochemical gradient. So this is a carrier. This, what you're seeing right here, is facilitated diffusion, which is the first step of secondary active transport. So now let's follow glucose. So I got glucose in through this carrier via facilitated diffusion, but now I need to get it into the bloodstream. So now I need to get glucose out, okay, into the extracellular fluid. How am I going to do that? Well, generally speaking, what you're going to have here is high glucose, and it's going to be lower here only because it's constantly being carried away by the bloodstream. So it doesn't like stay high in the extracellular fluid. So how do I get glucose to move from its high concentration to its low concentration? Will it move straight through the cell membrane? No, it's too big and it's water soluble. Will it move through a channel? No, that's the next cheapest, fastest way because it's too big. But it will move through a carrier. Okay, so I can diffuse glucose from high concentration to low concentration through a carrier. And what is that called when it does that? High to low through a carrier. It's called facilitated diffusion. Okay, and then once I get it out here, we don't really have to worry too much about transporting it into the bloodstream because, of course, it's fenestrated. So that takes care of glucose, and then now all I have to do is take care of the fact that if I move a bunch of glucose, I'm going to screw up my sodium concentration gradient. So I need to pump sodium back out, okay? And then sodium will diffuse into the bloodstream. So if you add in this first one and this second one, then sodium is absorbed via secondary active transport. I'm sorry, glucose is absorbed via secondary active transport. Okay, so this is glucose absorption. Glucose absorption is similar. You do amino acid absorption in a similar way, usually with sodium as well. So same way that you do glucose, you absorb amino acids at your gut. Secondary active transport. But then, of course, once you got glucose in, you also had to do a little extra over here, right here, with diffusing it out via facilitated diffusion. Okay, so the next one is here. Epithelial transport of water. This picture is terrible, but all it's saying is water is going to move as you move all of those solutes. So in this first picture right here, what they're showing you is a whole bunch of solutes being absorbed. It could be sodium or potassium or whatever. And then once you have done that, moved all of the solutes, then water is going to diffuse through aquaporins down water's concentration gradient. So it's really just osmosis. So as I move sodium, let's just say, let's go over here. As I move sodium, just as an example, as I move sodium from here to here all the way into the bloodstream, right? As sodium goes from high in the lumen to high in the intracellular fluid to high in the extracellular fluid, what it's doing is it's creating a concentration gradient for water. So as sodium goes from high one place to high one place, water goes low that place to low that place. So as sodium moves, water's concentration gradient is created. So sodium will move from the apical to the basal surface. It's generating an osmotic gradient, and then it pulls water through with it. So as my phys professor said, solutes suck, and water and sodium sucks the most. Okay, and then last one of the epithelial transports is just to talk about, well, what about lipids? How do you absorb lipids in the intestine? Well, remember, we absorb lipids not directly into the bloodstream, but into these little guys called lacteals, which are represented in green right here. So lipids are absorbed across the intestinal epithelium into lacteals, and it's primarily simple diffusion because, of course, they're lipid soluble. They're eventually going to be dumped into the bloodstream, but not immediately. Thus, as we said in the metabolism chapter, lipids avoid surveillance by the liver because they don't initially go through the hepatic portal system. Okay, so now, so that's it with the epithelial transport. In the next video, which will be the last of this set of notes, I'm just going to tell you guys a little bit about filtration, even though it's not in this chapter, but it really is a kind of epithelial transport, so I'll tell you about it.